Okay, so in the first video, I just talked about a general introduction to 1.6, and I said I would start doing examples, which I will, but I actually wanted to say something just to clarify something I said in the first video, which I said sometimes you can't separate the variables in a differential equation, which sometimes you can't. But in this section, we might be able to separate the variables, and we're going to be changing the form, the way our differential equation looks like to a different form, so that we are able to maybe separate the variables or use section 1.5. So I just wanted to, I don't know if that was unclear. So by, again, changing the form, or transforming, right, we may be able to separate the variables. Right, again, or use section 1.5 with our integrating factor. So again, dy dx equals f of xy, right? This is what we have, and we want to transform it to dv dx, v of x. Okay, that's a v, right? Where we are able to use section 1.4 and 1.5. Okay, so we want to use what we already know in the previous sections. So hopefully that's clear, just because when I listened to the video again, I really should have, I don't want you to think, well, you can't separate the variables ever. Well, you can, it just has to be, you might have to transform how the differential equation is presented. Okay, so now let's, I want to talk about a homogeneous first order differential equations, because that's what you're going to be starting with in this section. So a homogeneous first order differential equation, right, is of the form. Okay, so we have our dy dx, right, but it's going to be a certain form. It's going to be a function of y over x, and this capital F is not does not mean antiderivative here. It's just some function. It could be a radical function. It could be a polynomial function. It could be a rational function. We're going to definitely practice those different types of equations in the exercises. Okay, so if we have this, this is kind of the big picture here. When you have a homogeneous first order differential equation, what do you do? What if you can't, what if you try separating the variables, or looking for an integrating factor, and you're trying to solve for the solution, but it's just not working out? Well, you might have to substitute, and here's again kind of the plan. You are going to let v, right, because we want v, you're going to let v be 1 over x, right? That's your substitution, so I'm going to call that v. And that's going to be one equation that you're going to use. And notice that if you just cross multiply, right, you just basically solve for y, you have y equals vx. Okay, so that's the second equation. And the third equation that you're going to use is you're going to differentiate this equation with respect to x. And so the book skips a couple of steps, so let me just write those in. So ddx of y and ddx of vx. And so, right, ddx of y is just dy dx, right, which is our y prime. And then here, right, we're just using the product rule, right, to differentiate v times x. And when you do that, right, you just get v plus x v prime, or if you want to say times dv dx. But this is our v prime. And one of the nice things about a homogeneous first order differential equation is if I solve for x dv dx, I'll just write it, and I subtract a v from both sides, I get dy dx minus v. And in your book, right, your dy dx, and we know that's just really our f of y over x, right? Because that's what we named it in the beginning, right? My dy dx is this function of some, again, polynomial rational radical function where you want to utilize substitution. So our f of x is going to be, and let me just erase that. Okay, it's not letting me erase again. That's not equals. That's, right, minus v equals x dv dx. And I'm going to do an example that looks exactly like this with, actual, again, actual numbers. This is very general. But I wanted to really emphasize this because you're going to see it a lot, especially the first 5 problems of 1.6 homework. Okay, that is all I have to say about homogeneous first order differential equations for now.